This is a tutorial on permutations and combinations. First thing that we're going to talk about in this tutorial is the fundamental counting principle. To illustrate the fundamental counting principle, we're going to use the example that Dana wants to buy a new car. She's trying to choose between a Chevy, Ford, Mazda, or a Honda. Each vehicle can come in one of 6 different colors: black, green, blue, red, silver, or brown. So how many different combinations of vehicle and color does Dana have to choose from? Well, first Dana is going to choose between a Chevy, Ford, Mazda, or a Honda. If she chooses the Chevy, she has 6 different options for color. She can buy a black one, a green one, a blue one, a red one, a silver one, or a brown one. And she has these same 6 options for the other 3 types of vehicles. If we count up all these different options, we would find out that she has 24 different combinations of vehicle and color to choose from. Now, an easier way to do this might have been to take the different options she had for a car. She has 4 different options for a vehicle: Chevy, Ford, Mazda, or Honda. And then she has 6 different colors to choose from. And if we took the number of options for the type of vehicle and we multiplied it by the number of options for color, we would have found out that she has 24 different options. The fact that we can multiply these 2 options or choices together, that is the fundamental counting principle. The fundamental counting principle states that if an event can occur in P different ways and a second event can occur in Q different ways, then the amount of different ways that both events can occur is just P times Q. Well, our first event is the choice that Dana makes on what type of car she wants. She's got 4 different options when she makes that choice, so P is 4. The second event is choosing the color for her car. She's got 6 different options when she makes that choice, so that event has 6 different outcomes. If we take P times Q, we find out that there are 24 different outcomes for the 2 choices that she has to make. Now, the fundamental counting principle works if there are more than 2 events. If there are 3 or 4 events, then you just keep multiplying the different options for each event. So if there are 3 events and the third can occur in R different ways, then the 3 events can occur in P times Q times R different ways. So if she had 4 different types of cars to choose from, so 4 different possibilities in event 1 when she chooses her type of car, 6 different options when she chooses the color of her car, and then let's say she had to choose between a 2-door or a 4-door car. So there are 2 different styles of car. That means R would be 2. So the total number of options or possibilities for a different car that Dana could end up with would be 4 times 6 times 2, or 48 different types of vehicles, color and style including. So now let's talk about permutations. Permutations are when you look at all these different combinations of events, but the order in which these events occur is important. So here's a simple example of a permutation. There are 3 different color cars parked alongside of the road: a blue car, a red car, and a green car. how many different combinations are there for the order in which these cars are parked? Well, the blue car might be parked first. If the blue car is parked first, that means either the red car or the green car will be parked after it. Let's say the red car is parked after it. And that means that the green car must come next. So there's one possibility for the order in which the cars are parked. Now another possibility would be that the blue car is parked first, but then the green car follows it. And that leaves only the red car to be parked last. So there's another order in which the cars can be parked. Now what if the blue car wasn't parked first? What if the green car was parked first? Well, then the green car could be followed by the blue and the red, or the green car could be followed by the red and then the blue. Now the last two different combinations of how these cars can be parked would involve the red car being parked first. In one instance, the blue car would follow, and then the green car. The other option states that the green car would follow the red one, and then the blue. So there are 6 different combinations for how the 3 different cars can be parked. Now if you think of this as the fundamental counting principle, for the first car there are 3 different options. We could pick the blue one, we could have picked the green one, we could have picked the red one. But the second car in order, there are only 2 different options. Because if the blue car is picked first, then it can't be picked second or third. So if the blue one goes first, then the second one has to be either red or green. And then once the first 2 sets or the first 2 cars are decided, then there's really only one option for the third car. So think of this as P, Q, and R. So notice when we talk about a permutation, the options or the number of choices decreases with each choice. We go from 3 to 2 to 1. Well, a simple way to write this is called the factorial form. We would write this as 3 factorial, or 3 with an exclamation point at the end of it. This is called factorial notation. Here we have n with the exclamation point, and that just means n times n minus 1 times n minus 2 all the way down until we hit 1. So, if we were doing 3 times 2 times 1, where this is P, Q, and R, then we would just say 3 factorial because that's equal to 3 times 2 times 1. N would be 3, n minus 1 would be 2, and n minus 2 would be 1. Now if we had a bigger number, say 10 factorial, then that would be equal to 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, and 1. You always take it down to the 1. There is one special case where this isn't true, and that's when we take the factorial of 0. 0 factorial is always equal to 1. Now, permutations don't always have to use every available choice. Here we're told that 43 drivers compete in NASCAR's Daytona 500 race each year. So how many different combinations are there for the first 3 drivers to cross the finish line? Well, whoever comes in first place, that's 1 out of 43 drivers. So there are 43 different possibilities for the winner of the Daytona 500. So this would be P. Now Q, this is all the different possible combinations or all the different possible ways that somebody can finish second. Well, there are 42 different ways that some driver can finish second. There's 42 because whoever won or whoever came in first is no longer racing. So once somebody finishes first, then there are only 42 drivers left out on the track. And then for third place, say that's R, there would only be 41 drivers possible to come in third place. Now, if we multiply all these together, that means there are 74,046 different ways that the 43 drivers can finish first, second, and third, providing that every driver had an equal chance to finish first, second, or third. So here's an example of a permutation that doesn't use every driver or every possible situation, because we're not worried about who's finishing 42nd or 41st place. So how would we write this in factorial notation? Because 43 factorial, that's equal to 43 times 42 times 41 times 40 times 39, etc. But we don't want that. We just want 43 times 42 times 41. So to get rid of the 40, the 39, the 38, the 37, and everything that comes after it, the easiest way is to divide this by all the choices that we're not using. So there are 40 different drivers that aren't going to come in the first three spots. So we'll divide this by 40 factorial, because we'll be dividing this by 40 times 39 times 38, etc. And when you divide, the 40s will cancel and the 39s will cancel, and every other number all the way down to 1 will cancel, and we'll be left with just the 43, 42, and the 41. So that's how you can calculate a permutation where you don't have to use every possible outcome of each event. Now there's a specific notation in how to write permutations and a formula on how to solve them. Permutations are always written like this. There's a subscript n in front of a capital P followed by a subscript r. This is equal to n factorial over n minus r factorial. Now in our previous example with the NASCAR drivers, n would be equal to 43. R is the amount of positions or the amount of drivers that we're going to choose out of the 43. Well, we only want the drivers that are going to finish in first, second, and third. So R is equal to 3. So this would represent 43 P3. Or the permutation of 43 choices, choosing 3 of them. And this would be equal to 43 factorial over 43 minus 3 factorial, or 43 factorial over 40 factorial, which is exactly what we had before. Now the last thing we have to talk about is when we have permutations with repetition. What happens when some of the events can occur more than once? For example, how many different ways can the letters in the word feet be rearranged? Well, there's 4 different letters. There's F, there's E, there's a second E, and then there's a T. So I could rearrange this as F-E-E-T. I could also rearrange this as E, F, T, and then E. And then I could rearrange this and move the other E out front So there'd be an E, F, T, and E. But since these E's are the same, there's no way to distinguish between these two different choices. This is just a repeated choice. Well, there's a formula for figuring this out as well. And that formula looks like n factorial, and then we have s1 factorial times s2 factorial times s, and this is sk factorial. And what this means is that if we're trying to figure out how many different ways the letters in the word feet can be arranged, well, we're going to use every one of these letters. So we start with our n factorial, and in this case, since there are 4 different letters, so we would have 4 factorial. But then we would divide this by the number of occurrences to a factorial of each type of letter. So if S1 was equal to F, or we said S1 was the occurrences of F, well then S1 would be equal to 1 because there's only one F. So we would have 1 factorial. We would multiply that by S2, and we could say S2 is the number of occurrences that E occurs. Well, E occurs twice. So we'd multiply this by 2 factorial. And then lastly, we have a T, and T only occurs once, so we could say S3 was the number of times that T occurs, so we'd multiply that by 1 factorial again. This is equal to 4 times 3 times 2 times 1. Now 1 factorial is just 1, 2 factorial is 2 times 1, and 1 factorial is just 1. 4 times 3 is 12, times 2 is 24, times 1 is still 24. 1 times 2 is 2, times 1, and times 1 again is still 2. So there are 12 different ways that the letters in the word feet can be rearranged. So now let's try something a little bit harder. How many different ways can the letters in Mississippi be rearranged? Well, there are 11 letters, or 11 positions, for letters in the word Mississippi. So that means that N is going to be equal to 11. Now there are 4 different types of letters in this word. There is an M, there is an I, there is an S, and a P. Now if we say that S1 is the number of occurrences that M occurs in these letters. Well, M only occurs once, so there's only one M. If we say that S2 is the occurrences that I, or the number of I's that we have, well, there are 4 I's, so S2 would be equal to 4. If we say S3 is the number of S's, or the letter S, that we have in Mississippi, well then S3 is also equal to 4. And then lastly, S4, that's the number of occurrences, or the number of P's that we have to rearrange when we rearrange the letters in Mississippi. Well, there are 2 P's, or P occurs twice. So S4 would be 2. So if we go back to our formula, where we have n factorial over, in this case we'd have S1 factorial times S2 factorial times S3 factorial times S4 factorial. So we have 11 factorial over 1 factorial times 4 factorial times 4 factorial again times 2 factorial. Well, 11 factorial is 39,916,800. This is divided by 1 factorial, well that's just 1. 4 factorial would be 4 times 3 times 2 times 1. And 4 factorial again would be 4 times 3 times 2 times 1. And that's multiplied by 2 factorial, or 2 times 1. So we have 39,916,800 divided by 1 times 4 is 4, times 3 would be 12, times 2 would be 24, times 1 is still 24. 24 times 4 is 96. 96 times 3, 288. 288 times 2 is 576. Times 1 is still 576. Times 2 again is 1,152. And then times 1 is still 1,152. So 39,916,800 divided by 1,152 is 34,650. So there are 34,650 different ways that the letters in Mississippi can be rearranged. So now that we've talked about permutations, now let's talk about combinations. Combinations are just like permutations, except with combinations, the order in which we select something doesn't matter. Combinations are a collection of R objects selected from a larger group of N objects. So we want to know how many different combinations of R objects out of N objects. An example of this would be being dealt a hand of 5 cards. If I was dealt the ace of spades, the jack of spades, the 9 of spades, 7 of spades, and the 5 of spades, I would have the same poker hand as if I had been dealt the jack of spades, 9 of spades, ace of spades, 5 of spades, and 7 of spades. To me, the order in which the cards are given to me does not affect the value of the hand that I've been dealt. That's because these two hands are considered the same combination. So combinations, if you've studied permutations, are just like permutations, except the order doesn't matter. Now, if we wanted to calculate how many different combinations of R objects out of N objects selected, we could use this formula. N choose R is equal to N factorial divided by N minus R factorial times R factorial. Now, if you're not familiar with the factorial sign, this exclamation point, if you were told to find 7 factorial, well, 7 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. If you were told to find 4 factorial, you would take 4 and you would multiply it by 3 and then by 2 and then by 1. So whatever number is followed by the exclamation point or the factorial symbol, that just means you take that number and you multiply it by every integer that's less than that number all the way down to 1. A special rule for factorials, if you ever see 0 factorial, that's always equal to 1. Now let's try an example of trying to find a combination, or different amounts of combinations. Let's try to find how many different hands of cards can be dealt from a standard deck of cards. Now let's assume our standard deck of cards has 52 different cards in it. Then let's say our hand of cards is 5 cards. So we want to know how many different combinations of 5 cards can we get out of a standard deck of 52. So that means that our N is 52, and we're going to choose our value, or 5, out of that 52. So we're going to plug in 52 for N and 5 for R into this equation. This is equal to 52 factorial over N minus R, so 52 minus 5 factorial multiplied by 5 factorial. If we simplify this subtraction, this is the same as 52 factorial over 47 factorial times 5 factorial. Now 52 factorial, that's 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45, and so on, all the way down to 1. This is a huge number. This would take forever to calculate out by hand. But we don't actually have to calculate that entire quantity out. Notice that we're going to be dividing this by 47 factorial and 5 factorial. Well, for right now, let's forget about this 5 factorial. We'll come back to that. Let's just focus on this 47 factorial. This is another huge number. We're going to be dividing 52 factorial by 47 times 46 times 45 times 44, and so on all the way down to 1. Well, if I have a 47 in the numerator and a 47 in the denominator, that means I'm taking 47 and I'm dividing by 47. 47 divided by 47 is 1, so these terms are going to cancel. The same thing is going to happen with the 46 and the 45 and the 44, 43, 42, 41, all the way down to 1. All of those numbers occur in both our numerator and our denominator, so they're all going to cancel out. And all we're going to be left with is 52 times 51 times 50 times 49 times 48. And this, don't forget, is still divided by 5 factorial. So it's divided by 5 times 4 times 3 times 2 times 1. Now our numerator, if we do this multiplication, 52 times 51 times 50 times 49 times 48, that's equal to 311,875,200. Our denominator, 5 times 4, that's 20, times 3 is 60, times 2 is 120, and times 1 is still 120. So we have 311,875,200 divided by 120. That's equal to 2,598,960. That means that there are 2,598,960 different possible combinations of 5 cards that can be dealt out of a standard deck of 52. Now sometimes finding combinations are a little bit more difficult than that. Sometimes we have what we call multiple events. Here we're told that Tom and Jen decide to rent a movie. Jen wants to rent a comedy, but Tom wants to rent an action movie. So instead, they decide to each rent their own movie. The rental kiosk that they go to has 16 comedies, 10 action movies, and 14 dramas. So how many different combinations of 2 movies can they rent if they both get the type of movie that they want? Well, we say that this is multiple events because Tom is going to rent a movie, and then Jen is going to rent a movie. Tom is going to choose 1 movie out of 10 action movies. So the different combinations of Tom choosing a movie would be 10 choose 1. Now Jen's going to decide to rent her own movie, and she's going to choose 1 movie out of a possible 16 comedies. So Jen's combination of movies would be 16 choose 1. But what we're asked for is how many different combinations of the 2 movies that they're both going to rent. Now the movie that Tom rents is limited to the action movies, and the movie that Jen rents is limited to the 16 comedies. So the total different combinations of the 2 movies would be their different combinations multiplied together. If you're familiar with the fundamental counting principle, you know when you have 2 different choices, you can take all the different possibilities of each choice and multiply them together. And that's the same thing that's going on here. Now we just have to solve for 10 choose 1 and 16 choose 1. If you plug that into our formula, NCR is equal to n factorial over n minus r factorial times r factorial. For Tom's choice, this is 10 factorial over 10 minus 1 factorial times 1 factorial. And if you calculate this out, this is equal to 10. So there are 10 different possible combinations of choosing one item out of 10. If you do the same calculation for Jen's choice, well, there are 16 different ways she can choose one movie out of 16 movies. 10 times 16 is 160, so there are 160 different combinations of Tom renting an action movie and Jen renting a comedy. So remember, whenever you have multiple events, you take the different options and you multiply them together. But what if I said, since they wanted to rent different movies, they would together just rent at most 4 movies? Well, remember, there's 10 action movies, there's 16 comedies, and there's also 14 dramas. So there's a total of 40 movies to choose from. But if they rent at most 4 movies, that means they may rent 4 movies, or they may rent 3 or 2 or 1, or possibly they would rent 0 movies. Since the choice includes choosing movies out of a total of 40 movies, but they also don't know how many movies they're going to rent, instead of multiplying, we're going to add the different combinations. So we're going to say that out of 40, they may choose 0. And then we're going to add that to out of 40, they may choose 1. And we're going to add that to out of 40, they may choose 2. And then out of 40, they may choose 3. And then out of 40, they may choose 4. One key way to know that you have to add your different combinations instead of multiplying is when the problem tells you at most or at least. That is a big hint that you're going to be adding your combinations. Now we need to solve for all the different possible combinations of choosing 0 out of 40, 1 out of 40, 2 out of 40, 3 out of 40, and 4 out of 40. Now there's only one way to choose 0 movies out of 40. You just don't choose any movies. There's 40 different ways to choose one movie out of 40. If you calculate the rest of these out, there are 780 ways to choose 2 movies out of 40. There are 9,880 ways to choose 3 movies out of 40. And there's 91,390 ways to choose 4 movies out of 40. If we add all these up, that means there are 102,091 different possible combinations that they can rent at most 4 movies. And that completes the tutorial on permutations and combinations.